All right, so welcome back to the fourth and final installment of this mini course that Akhil Mathew has been giving. I really appreciate the effort that Akhil has been putting into these talks. So if you get a chance later, maybe send him a thank you or something, because he really appreciates we really appreciate the what he's contributed. Okay, and with that, I will let Akhil start.
Okay, thanks again. Thanks for everyone for coming back. So I guess today I thought we'd try to explain some of the ingredients that go into the work of Botmore and Schulze. So let's recall that one of the my pencil needs to be charged. So maybe I'll just say this in words. So let's remember last time talked about some of the ingredients such as derived Derived homology, and the cotangent complex, and topological Hochschild homology for certain large rings. So we talked about some of these ingredients last time, and today I guess I wanted to try to explain some aspects of the main theorem of Botmore and Schulze, which in characteristic P is saying that the sort of general homological construction of topological periodic homology, so that's the S1 Tate construction of THH, is something that you can use to recover crystalline homology. And as I guess I've sort of been alluding to, it's also it's possible to use this, a formally very similar construction. There are going to be some additional complications. So you have to, there are going to be some additional technical complications, but it's possible to follow much of the formal strategy to define homology theories, so analogs of crystalline homology and mixed characteristics. That's maybe the real main goal of what BMS are trying to do. So that does involve some additional technicalities. I wanted to focus on the characteristic P case because the construction is a little bit more direct. So let's maybe state the theorem. So theorem. Morrow and Schulze. So R is going to be a smooth algebra over a perfect field. So K is a perfect field of characteristic P. P is greater than 0. And then the statement is that this construction TP of R, defined to be the S1 Tate construction of THH of R, has a filtration whose associated graded is to periodic crystalline homology of the ring. So let's recall also the crystalline homology, that this is a theory. I didn't say too much about it, but it's an integral version. This theory here is an integral version of Derived homology. And so, for example, it's quasi-isomorphic to the Derived complex of R tilde over the Witt vectors of K, p-adically completed, whenever R tilde is a lift of R to the Witt vectors of K. So maybe, sorry, we can even assume K as FP, and then the idea is that you look at the p-complete Derived homology of a lift of your algebra. You have an algebra over FP. You choose some flat lift as ZP. Take the completed p-completed Derived complex, and the claim is that that's actually a functor in R. That's this crystalline homology construction. Right, so the claim is that this TP of R is filtered by crystalline homology. And well, I guess so this construction works in mixed characteristic, and you can use it to define new homology theory. So in particular, the idea is that this construction of the filtration is something very general. And I guess if you wanted, you could even use this as a definition of the right-hand side. So I guess I wanted to explain some of the ingredients that go into this, into defining this filtration. So maybe I should also say that this is supposed to be analogous. To the motivic filtration on algebraic K theory. which starts with where, well, algebraic K-theory has a filtration whose associated gradient is given by, which have that homology, and it's supposed to be something analogous. It's in some ways supposed to be analogous to that. So it's a very different type of setup. So this is no longer, for example, this is no longer something which is A1 invariant like algebraic K-theory for smooth rings. So it's sort of analogous, but not entirely clear what that analogy is, I think. So I guess, yeah, I wanted to explain some of the ingredients, and so even outside the statement of these theorem or proving this theorem, I think some of these ingredients are pretty useful tools and might be useful for other things as well. So ingredients in the proof. Yeah, so I should say that also the construction of this filtration is sort of very different from things people do for K-theory. So ingredients in the proof of this theorem. So I guess one of the ingredients is this technology of derived functors, which I talked about last time. So last time I talked about, so the idea is that you want to prove something for smooth algebras, but you're actually going to prove it by working not with smooth algebras, but with these very large rings. And then you have to derive your functors properly. So last time we talked about the machinery of derived functors. And derived Derived homology. So examples were derived Derived homology, which is the derived functor of the Derived complex, and also the cotangent, the Quillen cotangent complex. And so recall that these derived functors have the property that if you plug in a polynomial ring, they're just the usual thing. And in general, you compute them via some simplicial resolution. So we consider derived Derived homology. So let's call that dr over k, and the cotangent complex L of something over k. Okay, so we talked a little bit about this last time, and using this technology, we proved the following sort of proposition, which is that if R over k is any algebra, then there is a filtration on the Hochschild complex of R over k whose associated graded is given by, well, the ith associated graded is the ith wedge power of the cotangent complex of R over k, and then shifted by I. So, right, so here, this wedge power is in the derived category of R modules, so it's some derived exterior power, and then you have the cotangent complex showing up. And so this was something that is sort of a very formal consequence of this machinery, and the proof is, well, this is just a Postnikov filtration if R is smooth, and then you take derived functors everywhere. So it's a Postnikov filtration for R smooth, and then take derived functors everywhere. And the idea is that you can use this, that there are lots of non-smooth algebras where you actually know the cotangent complex, and you can use this to compute their Hochschild homology. So an example from last time is that the Hochschild homology of R over k is just R itself if R is a perfect ring, perfect FP algebra. And I guess the base k is also a perfect field. So this is already an example where we can say something for sort of a big ring. So let me explain sort of one of the things that this machinery buys you, and this is one of the starting points for the paper of the BMS paper, which is the following sort of the surprising theorem. So the theorem of BMS, which is actually, sorry, so I'm saying this because it's based on this proposition. It's based on this proposition saying that you can build a Hochschild complex out of the cotangent complex, and the theorem is that the construction which sends a ring R to its topological Hochschild homology.
Akhil?
Yes?
The Hochschild homology of R over K, how is K related to FP in the example?
Sorry, so K is any perfect field, characteristic P.
And
so it doesn't
R
have to be FP. So, sorry, so R is a perfect FP algebra?
Yeah, I see. Thank you.
Yeah, so both sides are perfect. So I guess what's nice about perfect rings is that when you're doing something like Hochschild homology or the cotangent complex or something, it doesn't really matter what the base is. sorry, so maybe I should, well, before I state the BMS theorem, let me just mention sort of a consequence of this, which is actually also important. So corollary, if R is a perfect FP algebra, then you have the same result as Hochstadt's theorem. So the topological Hochschild homology of R is given by R bracket sigma for sigma integrate 2. So a consequence is that Hochstadt's theorem is going to work not only for FP, but for any perfect FP algebra. And that's sort of one of the sort of miracles in this type of business in characteristic P. So that if you're working over a perfect base, it sort of doesn't really matter what the perfect base is, and you can oftentimes results are just going to be uniform for all perfect rings. So perfect rings have this sort of miraculous property. Perfect rings have this sort of miraculous property that their entire cotangent complex is contractible, cotangent complex over FP. And that's something that's sort of a miracle in characteristic P that I think there's no analog in characteristic 0. Okay. But so this ends up being a corollary, and that's because, well, because of this sort of slogan, maybe from the first or second talk, that if you take THH, then it's sort of a one-parameter deformation of Hochschild homology. So more precisely, you take the cofiber by sigma, that's the same as the Hochschild homology of R relative to FP. And well, we just said that that's R. And then, so that forces THH of R to be R bracket sigma. Okay, so there's a version of Hochstadt's theorem for any perfect ring. So that was sort of the first application that we're ending last time with. But one of the things that is really crucial about this, this fact, this proposition, so you might call this filtration the HKR filtration. It's not something that you have to do too much work to construct. It's just a Postnikov filtration of a smooth case and then derived functors. But it already sort of buys you some non-trivial calculations. And it also buys you this theorem of BMS, which is a little bit, slightly surprising theorem, and it's really important for defining these filtrations. So the theorem is that the construction that sends R to THH of R satisfies faithfully flat descent. And so as does the construction R maps to TP of R, which is THH of R Tate S1, or also, TC minus of R. Well, maybe I didn't define that. So TC minus of R is THH of R, S1 homotopy fixed points. Essentially, all of these constructions that you can build out of THH in a simple way that you want to work with, and maybe the most important for us today is TP of R. The claim is that this satisfies faithfully flat descent. So more precisely what that's saying, if you have a faithfully flat map of rings R to S, then you can recover TP of R as the totalization of a cosimplicial object, namely TP of S. So that maps in two ways to TP of S tensor RS, and you get a big cosimplicial object. And the claim is that converges to TP of R. So TP of R is the totalization of this big cosimplicial object. So if you know TP of S and if you know TP of all these relative tensor products, then well, maybe up to a spectral sequence, you know TP of R. So maybe I should also say that so remark is that in the Atal case, this is due to Weibel and Geller, and also McCarthy and Manesian. And so the Atal case is a little bit simpler because then you actually have some sort of base change formula. So you can actually describe THH of S in terms of THH of R. But in the general faithfully flat case, you don't have such a statement. So you have to give a different argument. There's no sort of direct relationship between THH of R and THH of S if you just have a flat map of rings from R to S. But nonetheless, the statement is that you have this descent theorem. So yeah, so this is one of the first things that BMS proved. And maybe I should just say the idea. So the idea is to first prove this. So I think this was actually first observed by Bott. Is first prove this for the cotangent complex. So it's a little bit hard to sort of deal with THH directly. So first you prove this for the cotangent complex, for the functor cotangent complex over some base. So maybe, so I don't know. Let's say we're working with FP algebra. So first prove it for the cotangent complex relative to FP. And here the idea is that this is actually not too complicated. So here you use the fact that you have some extra tools for working with the cotangent complex. So you have so you use general sort of cofiber sequences that you have for the cotangent complex. So the cotangent complex has this property that, like, if you have three rings, if you have a sequence, a triple of maps of rings, then you get a cofiber sequence involving the cotangent complex. So maybe more precisely, if A to B to C are maps of rings, then you get a cofiber sequence where you have the cotangent complex of B over A, derived tensor from B up to C, mapping to the cotangent complex of C over A, mapping to the cotangent complex of C over B. So, so this is one of the basic properties of the cotangent complex, and this lets you treat the case of the cotangent complex sort of pretty formally. There's some argument to do, but you have this extra tool that comes from the cofiber sequence, and then you bootstrap from the cotangent complex to its wedge powers. So bootstrap to wedge powers of the cotangent complex, and show that this construction is also a sheaf. For the flat topology. So the idea is that you want to show that some construction like TP is a sheaf for the flat topology, and the idea is that you do all of this by breaking it into building blocks, which are simpler, and then proving it for these building blocks directly. And so the building blocks are the cotangent complex and its wedge powers, and then you sort of show that directly using these cofiber sequences. So then you use so now we've shown that the cotangent complex, so now Bot shows that the cotangent complex and its wedge powers are sheaves for the flat topology. But now you use the HKR filtration, which tells you that Hochschild homology is filtered by these wedge powers of the cotangent complex. So now you use the HKR filtration, and then you conclude that the Hochschild complex, let's say relative to FP, is also a sheaf for this topology, just because it's built out, as an inverse limit of these sheaves given by wedge powers of the cotangent complex. And then finally, well, you have Hochschild homology, and then finally you get up to topological Hochschild homology. So THH of R mod sigma is HH of R relative to FP. So you can also, you can do sort of a box-time spectral sequence. THH of R mod sigma is Hochschild homology, which is a sheaf. And then inductively, THH of R mod sigma to the n is a sheaf. And then taking the inverse limit as n goes to infinity, which is going to be defined by connectivity, is going to tell you that THH of R is a sheaf. Oops. So this is going to imply that THH of R is a sheaf. And then finally, you have to argue that you can pass S1 tape constructions through the fact that everything is a sheaf. And again, this is not so hard. There's a little bit of a connectivity argument that one has to make. So in the end, it's sort of a pretty formal argument, but the key step is that you reduce everything to the cotangent complex, and then sort of really bootstrap from there. So this is sort of one of their key ingredients, that TP is a sheaf. Okay. So now I want to explain how this is used. So in fact, their filtration on TP is defined via some sort of sheafification procedure. So let's now say R is a smooth. Let me just say for simplicity, it's a smooth FP algebra. So the idea is to use the sheaf property to get at TP of R. So what we need is we need to find a big faithfully flat extension of R for which we understand TP pretty well. And so here's the construction. So the construction is that I'm going to let S to be the perfection of R, the direct limit perfection of R, which is defined to be the colimit of copies of R along the Frobenius map x goes to x to the p. So this is a construction which starts. So this is some general construction which starts with an FP algebra and produces a perfect FP algebra given by taking the directed limit of Frobenius acting over and over. So maybe just example to keep in mind. I mean, throughout the example to keep in mind is a polynomial ring of p brackets x, and then this perfection R perf is, it's now what you might write as fp brackets x to the 1 over p to the infinity, which is the directed union of polynomial rings in the variable x to the 1 over p to the n. So the idea is you want to understand TP of R. Well, you want to do it through this sort of Chakner type construction. You want to do that through this finding an S which is much bigger than R for which you can understand TP of S, and then using this sort of typicalization. Okay, so the strategy is that specifically you're going to take S to be the perfection of R, which is this colimit along Frobenius of R, and this is a construction which always produces a perfect ring. So example is fp brackets x to fp brackets x to the 1 over p to the infinity. And now it's a basic fact that if R is a smooth algebra, then the map from R to its perfection, which I'll call S, is faithfully flat. In fact, it turns out this is actually a characterization of smoothness. But yeah, you can see this directly from in the polynomial ring. So the map from the polynomial ring to the perfect polynomial ring is a faithfully flat map. Okay, so now to describe TP of R, to describe and ultimately give this filtration, it suffices to understand TP of S, TP of S tensor RS, and all of these iterated properties. So let's start with the first one. So the first case is going to be the easiest, is TP of S. Sorry, and I should say that although these tensor products of S, S tensor S, and so forth, the idea is that these are going to actually be easier than TP of R directly. And what do I mean by easier? For example, they're going to be concentrated in even degrees. Okay. So the first case, right. So the first case is TP of S, and remember now that S is a perfect FP algebra. The Frobenius is an isomorphism. And now we have the following general proposition: we can compute TP of any perfect FP algebra. So I think, I explained the formula for TP of FP, but actually there's a formula for TP of any perfect FP algebra. So proposition, if, well, S is a perfect FP algebra, and then TP of S is 2 periodic, and in degree 0 you have the Witt vectors on S. It's 2 periodic, and the periodicity generator is coming from the fact that it's an S1 Tate construction, so it's coming from the circle. Right. And so the theorem is that in degree 0 you have the Witt vectors, and then it's just 2 periodic. That's all there is. So the proof is actually, this is similar. It's essentially the same as what happens for FP. So it's analogous to what happens for FP. And the reason is, well, what I wrote down earlier. So THH of S is this ring S bracket sigma. THH of S on homotopy groups is this ring S bracket sigma for sigma in degree 2. So that's something that came from the vanishing of the cotangent complex for perfect rings. That's something that, is not totally obvious that we sort of proved using the HKR filtration. But it's true. And then, well, so you have the analog of Buckshot theorem, and now you run the S1 Tate spectral sequence. So run the S1 Tate spectral sequence. Run the S1 Tate spectral sequence. There's no room for differentials. So everything, you're starting with something which is in even degrees, THH of S, and you're taking an S1 Tate construction. Everything is in even degrees. So there's no room for differentials. So it's only need to identify the extensions. And the claim is that the extensions are sort of as non-trivial as possible. So that's why you're getting the Witt vectors of S in degree 0. And it's sort of the same thing that happens for FP. The claim is the same sort of thing. Okay. So that's sort of really nice. It's telling us that, TP of R is going to be something that's, it's something related to crystalline cohomology of R. So it's going to have a lot of odd degree stuff, a lot of even degree stuff, and, things are going to talk to each other in ways that might be a little bit subtle. But what this is saying is that when you go all the way up to the perfection, when you perfectify, then you have something which is only in even degrees, which you would expect is sort of easier to work with. So in fact, the way that you define the filtration is, well, I'll just say it now and maybe write it later. You just define it on TP of S tensor RS and so forth. It's just a Postnikov filtration there. Because everything is in even degrees, you just use a Postnikov filtration. And then you totalize, and you get something which is very much not the Postnikov filtration on TP of R. Okay. So the filtration, the analog of the BMS filtration on TP of S is really easy. It's just a Postnikov filtration. And maybe it's worth also saying that the crystalline cohomology of S is the vectors of S. Okay, so that's the first step. But so for perfect rings, things are pretty concrete. But unfortunately, what's going to happen is we need to understand not only TP of S, but also TP of S tensor RS, and all of these, this whole check nerve. So unfortunately, this is not sufficient. So unfortunately, this is not sufficient, because we also need S tensor RS, S tensor R, S tensor RS, and this whole check nerve. And well, the problem is S tensor RS is not a perfect ring. So S is a perfect ring, so we're taking the tensor product of two perfect rings, but we're taking the tensor product over R, which is not perfect. So what's going to happen is that this S tensor RS is not quite a perfect ring, so the answer is not going to be quite as simple. So maybe just to illustrate this, let me do the example. Let's look at the example again of the polynomial ring. So let's say R is FP brackets X. So S is the ring FP brackets X to the 1 over P to the infinity. So if we're trying to describe TP of R, well, then we run into the ring S tensor RS, which is, well, it's FP. We have to take the tensor product of two copies of S. So that's FP brackets X to the 1 over P to the infinity. Well, let's say X1 to the 1 over P to the infinity and X2 to the 1 over P to the infinity. But we're tensoring over R, so we have to mod out by the relation X1 equals X2. So for example, if we consider the relative tensor product, S tensor RS, in this case, where R is FP brackets X, we get this funny ring. Well, first we get a perfect polynomial ring in two generators, X1 and X2, but then we impose the relation that X1 is equal to X2. So note that this does not imply that X1 to the 1 over P is X2 to the 1 over P. So this is no longer a perfect ring. It's a ring where it is a quotient of a perfect ring. It's a quotient of the perfect polynomial ring in two generators, where we're quotienting by a single element. But it's no longer a perfect ring because you can consider the element X1 to the 1 over P minus X2 to the 1 over P, and its P power is 0. But the element itself is not 0 in this ring. So instead, what's going to happen is that S tensor RS is a so-called regular semi-perfect ring. Which means that it's not quite perfect, but it's the quotient of a perfect ring by a regular sequence, be at least Sariski local. Right. So that's what's happening over here. You're taking the quotient of the perfect polynomial ring in two generators, but then you're quotienting by the regular element X1 minus X2. So these tensor products S tensor RS, they're going to be these so-called regular semi-perfect rings. So more generally, this is going to be the case for all the tensor products are going to have this property that they're regular semiperfect. So I'm going to underline that. Okay, so what this really boils down to is that one needs to understand first of all, one needs to understand the topological periodic homology of, sorry, not TP of S, TP of, let me give it a different name, TP of T, let's say, where T is a regular semiperfect FP algebra. And so this is something that's going to be a bit more complicated than just the Witt vectors of a perfect ring. And well, ultimately, we're interested in relating this to some sort of crystalline cohomology. So we should relate this to the derived, we should understand the derived crystalline cohomology of T. And the main theorem, well, the main theorem is going to be that, well, technically up to a mild completion, but it's not going to be very important. Sorry, up to a mild non-complication completion. The derived crystalline cohomology of T is just a discrete ring. It's, I mean, a priori it's an infinity ring spectrum, but it's just, it turns out just to be a discrete ring. And TP of T is the two periodic version of this. And homotopy groups is two periodic derived crystalline cohomology. So the idea is that, again, we want to relate TP of a smooth algebra with crystalline cohomology. And the idea is, well, instead of doing that, let's relate TP of a regular semi-perfect ring with now the derived crystalline cohomology of that regular semi-perfect ring. And then by using faithfully flat descent, really faithfully flat descent of TP, but also something for derived crystalline cohomology, that's going to give the answer for smooth algebras. So this is sort of the heart of the argument, which is that one needs to describe topological periodic homology for these so-called regular semi-perfect rings. And these are the rings that show up when you try to do faithfully flat descent from a smooth algebra to its perfection. And the main theorem is that you can see everything. You can see everything directly on homotopy groups there. And the BMS filtration, so then given the theorem, the definition is that the BMS filtration on R on TP of R, where R is your smooth algebra, is defined as, well, you take the Plotnikov filtration on this check nerve and then totalize. So let's say F upper I of TP of R is tot of tau less than or equal to 2I TP of S, mapping it in two ways to tau less than or equal to 2I of TP of S tensor RS, and dot, dot, dot. So you're just looking at the Plotnikov filtrations of TP of the perfect ring S and of these regular semi-perfect rings given by relative tensor products of S over R. Also, because everything is in even degrees, the Plotnikov filtration is indexed by 2I instead of I, because everything is anyway in even degrees. And then so basically, this definition works and gives you something. Gives you the filtration whose associated gradient is derived crystalline cohomology by this sort of explicit calculation that you have to do for regular semi-perfect rings. Sorry, so this gives a filtration on TP of R, and the fact that it's associated graded is crystalline cohomology follows from the analogous assertion on TP of, well, all of these relative tensor products of S. So it follows from the fact that TP of these regular semi-perfect rings can be described in terms of the derived crystalline chronology. Okay, so this is basically this strategy. But yeah, so I guess what I wanted to do is to try to say something about how about what these regular semi-perfect rings look like and what they give you. So, oops, sorry. So how do we work with regular semi-perfect rings? Right. Okay, so right. So this is the question. Right. So maybe I should say sort of so in particular the theorem is saying that if you have a regular semi-perfect ring, you still have this sort of evenness phenomenon that TP and also THH and all of its variants are concentrated in even degrees. So ultimately that boils down to a fact about the cotangent complex. So the claim is that TP, etc., are all in even degrees. And this boils down to a claim, ultimately everything is built from the cotangent complex. So this all boils down to the cotangent complex of L of T over Fp. And so the proposition is that if T is regular semi-perfect, then the cotangent complex of T over Fp is it's the suspension of a finitely generated projective T module. So recall, so this is sort of what's a little bit surprising. So in particular, it's all in degree 1, all in homological degree 1. So this is sort of what's maybe a little bit surprising, a little bit unfamiliar. So if you're used to thinking about the cotangent complex, well, then maybe you know that for smooth algebras, the cotangent complex is just differential forms, and so it's a projective module in degree 0. It's a discrete thing. But what's sort of remarkable is, well, as we saw a little bit last time, when you have a perfect ring, then the cotangent complex just goes away completely over Fp. So when you go up to the perfection, the cotangent complex completely disappears. If you have a regular semi-perfect ring, which is the more general thing we need to consider, then the cotangent complex is still pretty controllable. It's no longer just a module in degree 0. But now it's shifted by 1. It's not something that's too messy homologically. It's just a suspension of a finitely generated projective T module. And so basically it's going to have T as a quotient of a perfect ring by some regular sequence, and you're going to get one generator of this projective T module for each element that you're modding out by. So this is maybe the starting point. So in particular, it's in regular semi-perfect rings or another class of rings for which you can really control the cotangent complex. Right, and so then a corollary of this is that the Hochschild homology, so T is again regular semi-perfect. And the consequence is that Hochschild homology of T relative to Fp, and similarly the topological Hochschild homology of T are all in even degrees. So this should be a little bit surprising because, again, if you're used to thinking about smooth algebras, then smooth algebras have the property that their Hochschild homology is basically differential forms. So of course there are I forms for I odd. So there are 1 forms on your algebra, and so that's going to contribute to the Hochschild complex in degree 1. But what's sort of surprising is that when you're in this regular semi-perfect case, you only have contributions in even degrees. But this also turns out to be sort of a formal consequence of the HKR filtration. This turns out to be a formal consequence of the HKR filtration. And the reason is that, well, the Hochschild complex of T over Fp is filtered by terms whose associated graded looks like wedge I. So it's filtered, and ger I is wedge I over T of the cotangent complex of T over Fp. But now what's happening is that the cotangent complex, the cotangent complex of T over Fp is given by the suspension by one of a projective module, of a finitely generated projective module, just an ordinary finitely generated projective T module, and then you suspend it by one, and then you get the cotangent complex. So ger I, I'm sorry, this should be shifted by I. Okay. So ger I then becomes wedge I over T of P shifted by one, and then you shift it by I. So just by this HKR filtration. But now sort of something really nice happens. So normally this contribution of this ger I is going to give you stuff in degree I because you have I forms in degree I. But here you're taking the ith wedge power of not an ordinary projective module, but a projective module shifted by one. So the fact that you have this extra shift by one that's showing up is really going to sort of save things. And this turns out to be the same as the divided powers, T divided powers of P shifted by I, and then shifted by I again. So this last fact is using a formula for how to compute, formula due to Elucy, of how to compute the ith wedge power of a complex of a module, just a projective module. If you're shifted by one, you can compute its exterior powers, and they're the divided powers of the original algebra, but with some extra shift. So in particular, you get that this is gamma. So in particular, you get that this is the ith divided power of P in degree 2I, and so in particular, it's all in even degrees. So in particular, what you find is that the Hochschild homology of T over Fp is given by the divided power algebra for T on this projective module P, where P has degree 2. So that was so again, the idea is that when you have a regular semi-perfect ring, then the cotangent complex gets shifted by one, and then by this HKR filtration, that puts the Hochschild homology, that turns the Hochschild homology, instead of being an exterior algebra in differential forms, now it's a divided power algebra on something in degree 2. So you get this this sort of really nice fact that Hochschild homology is in even degrees, and this also implies, for sort of formal reasons, sort of the Bockstein spectral sequence, that THH of T is even. And then you can take S1 Tit construction. So again, that's going to take even things to even things. So also TP of T is even. Okay. So that's sort of the first step. But then ultimately, okay, so first it's all in even degrees. That's by this cotangent complex stuff. But then you actually want to identify these rings. So now you know it's in even degrees. You actually want to say what it is explicitly. And related to derived Derived homology. So let me just tell you what the answer is. So the answer is that if T is a regular semi-perfect ring, then the derived crystalline homology, so let's call that L Chris, derived crystalline homology of T. Sorry, this is probably not standard notation, but let's just use that for now. Then the derived crystalline homology of T is just a ring in degree 0. Is a discrete ring in degree 0 And it's something, it's a ring that has a name. It's a ring called acris. So I'll say what acris is in a second. It's a ring called acris of T. So moreover, TP of T, so TP in degree 0 of T, so TP is 2 periodic, we've just seen, and it has no odd dimensional stuff. So TP 0 of T is the completion of acris of T with respect to something they call the Nygaard filtration. Right, so sorry, so this is due to BMS. Okay. So they explicitly identify both the topological periodic homology and the derived crystalline homology with a construction which I think is familiar to, is a construction, pre-existing construction of Fontaine, called this ring acris. So maybe in the rest of the talk, I want to say something about what this ring acris looks like. Well, ultimately, I guess I should say that what's going into this proof. What's going into this proof is some explicit calculations you have using the cohesion complex. Essentially, you sort of using the types of ingredients that we've been talking about, that you can filter. You can filter all of these rings using spectral sequence, using the S1 Tate spectral sequence, using the HKR spectral sequence, so on and so forth. So you get a filtration, but then you have to identify the ring as a whole. There's some work involved in there, but you can use universal properties of these rings to do that. So this is sort of the key technical point of BMS and what leads to the BMS filtration. Okay, so let me say something about what this ring acris. So this is a somewhat, it's a somewhat large construction. So T is already, it's a pretty large ring. It's a regular semi-perfect ring. So T could be something like, e.g. T could be something like the ring FP brackets x to the 1 over p to the infinity mod the element x. That would be an example of a regular semi-perfect ring, the type of ring that we might feed into this. An acris is going to be some machine which takes this big regular semi-perfect ring and produces, so semi-perfect ring in particular, it's in characteristic P, and acris is going to produce something which is p-adically complete, but which is not p-torsion. So it's going to produce, it's going to be essentially that, well, it's a derived crystalline homology of T. Yeah, so let me say what that is. So construction of acris. Right. So first we have T, which is this regular semi-perfect ring. And what we're going to do is we're going to consider the inverse limit perfection of T. So this is inverse limit along the Frobenius map, x goes to x to the p, of copies of T. So this earlier discussed a way of taking a ring and producing a perfect ring, which is to take the colimit along Frobenius. But there's also sort of a dual construction of starting with a ring and producing a perfect ring, which is to take the inverse limit along Frobenius. And so, for example, this construction, if you start with FP brackets x to the 1 over p to the infinity mod x, this inverse limit perfection construction is going to produce the x-adic completion of the ring x FP brackets x to the 1 over p to the infinity. So, example of this construction. So it's an inverse limit construction. And so then the next step is to take the Witt vectors. So consider the map from the Witt vectors of T upper perf to T. So this is a map which I guess is often called theta. And the idea is that theta is, T is a regular semi-perfect ring. The idea is that theta is the universal pro-nilpotent thickening of T. So for example, if you have a perfect ring, you just take its Witt vectors, and that's some sort of, well, let's say p-adically complete. You take its Witt vectors, and that's sort of its universal p-adically complete thickening. It's something such that when you reduce mod p, you get the perfect ring again. If you have a ring which is not perfect anymore but semi-perfect, there's still an analog of this construction, but you have to first pass the perfection. So it's a universal pro-nilpotent thickening of T in the sense that if I have any map S to T, which is a nilpotent thickening, then there's a canonical map. There's a canonical lift from the Witt vectors of T upper perf to S. So it's sort of the initial object in some sort of pro sense in the category of nilpotent thickenings of T. And then the definition is that, right, so the definition is that a cris of T is the divided power envelope of the map theta. So it's what you get by starting with, so you start with this universal pro-nilpotent thickening and formally add all divided powers of the elements in the kernel. So start with the Witt vectors on T perf and add all divided powers of elements in the kernel of theta. And right, so divided powers means that you're adding elements of the form x to the I divided by I factorial whenever x is in the kernel of theta. But we're going to make this compatible with divided powers on P. So P to the I divided by I factorial is an integer, and that's supposed to be, when you're formally adding elements x to the I over I factorial for x in the kernel of theta, well, that should be compatible with how you take P to the I over I factorial. So the idea is that this ring A cris of T is the universal, it's a universal, well, again, in a pro sense, it's a universal pro-PD thickening of T in the sense that if I have a map S to T, which is a nilpotent thickening, with divided powers on the kernel, then, well, there's a natural map, first of all, from A cris of T back to T, but then the claim is that that naturally maps lifts to S. So it's, I don't know, it's sort of a big ring theoretic construction that I think plays a role in parts of ecology theory. But the calculation that one does is that it's something that shows up when you consider topological Hochschild homology. So this construction of the universal PD thickening of the regular semi-perfect ring is exactly what shows up when you think of the topological periodic homology of T. It's also what happens when you think of the derived crystalline homology. So this is, I guess maybe this is not so surprising if you're thinking of, if you're thinking about crystalline homology. Crystalline homology is already something that's sort of built using a site where divided powers are sort of part of the game. So this is sort of, well, I guess depending on your definitions, maybe this is even sort of immediately clear that this is the crystalline homology of a regular semi-perfect ring, that it's this ring A cris. You have to be a little bit careful with the fact that everything is derived here, that you're doing this Kohn extension process. So maybe that's not so surprising that you'd have something that has to do with divided powers. But maybe it's a little bit more surprising that if you consider TP of these large rings, if you consider TP of T, then this is closely related. This is actually a certain completion of this ring A cris of T, and its completion with respect to a filtration called the Nygaard filtration. It's essentially a filtration based on, it's a filtration by ideals based on how divisible the Frobenius is going to make you, how many powers of P are going to show up when you take Frobenius of an So the theorem that one has to do is to show that TP of T is naturally a crys of T. Well, so for example, in degree 0, maybe I should say something about this. So in degree 0, well, TP of T is the same as TP of 0. T is the same as pi 0 of THH of T S1 homotopy fixed points, which maps now to pi 0 of THH of T, just forgetting that it's an S1 homotopy fixed point, and this is the same thing as T. So whatever this ring TP of T0 is, it maps back down to T, and then somehow, I guess the argument is that this ring has divided power. So you have a map, you have some ring which is some sort of pro-nilpotent thickening of T. TP of T sub 0 is, by sort of formal reasons, it's a pro-nilpotent thickening of T. And what you have to do is show that it's got divided powers on the kernel. You got to show in some way that the kernel has divided powers, and also that it's complete for this filtration. So I think the idea there is that you can sort of see that the divided powers showing up by thinking about by sort of calculating explicitly in certain examples and seeing them as sort of the same divided powers that show up in the homology of CP infinity, in the homology of CP infinity. So so I guess I'm about out of time, so maybe I should just wrap up by saying that yeah, so there are analogs of, this is sort of a very general construction. So just to so even if you didn't, we're familiar with crystalline homology, the idea is that, maybe the key takeaway from this is that if you're working with smooth algebras, it's sort of helpful to work with these large algebras, these regular semi-perfect rings. And for these regular semi-perfect rings, everything is naturally bumped into even degrees. So instead of stuff in both odd and even degrees as for smooth algebras, everything is in even degrees. And at least for FP algebras, you can really sort of control it pretty explicitly, well, maybe somewhat explicitly using these large rings A crys. You can work out what TP and THH and so forth are. So the idea is that much of this type of procedure carries over to mixed characteristic. But in mixed characteristic, there's sort of one of the main wrinkles is that in characteristic P, you have this canonical resolution. You have a smooth algebra R, you map it to its perfection, you consider the check nerve. There's a canonical way of starting with a smooth algebra and making it perfect. So I guess the issue in mixed characteristic is that there's sort of no analog of that canonical check nerve construction. So one of the things that BMS developed is that they developed something that there's no sort of canonical check resolution. So that BMS developed something called the quasi-symptomic site. And it's a site-theoretic approach of basically making the above work in mixed characteristic. So in mixed characteristic, you're starting with a ring like, let's say, ZP brackets T, everything is P completed, but now you want to map it to a much larger ring. So first you want to replace ZP by its completed integral closure. So it's completed absolute integral closure, and then you want to add all the P power roots of T. So this would be a ring R, and this would be a ring S. And the idea is that similarly you can sort of describe THH, TP, and so forth, not for R explicitly, but maybe for S tensor RS, and so forth. But the problem is that there's no sort of canonical way of going from R to S, so you have to introduce this machinery of the quasi-symptomic site. But so it is possible to do this and to define filtration in this way. And then in doing so, you get sort of new p-adic homology here. So yeah, so thanks a lot. Thanks a lot for the opportunity to do this. This is really fun. And thanks to all of you for sticking with it and for coming. So yeah, so I think I'll end here. Thanks.
Okay, and are there questions? Or I'm going to mute people.
I also have that question.
Okay, sorry, I muted everyone. So if you have a question, you can go ahead and unmute your mic and ask.
You mentioned at the first lecture that one of the nice consequences of making new cohomology theories was to count points. Is
Right.
there, now that we know more about making these new homology theories, are there concrete applications we could talk about in more detail?
Well, I guess I think I mean these are homology theories and mixed characteristic, and if you're counting points, presumably you're over a finite field, and so you can count points using crystalline homology. And my understanding is that people have used techniques in p-adic Hodge theory to actually make point counting statements. So, sorry, I can dig out a reference. Don't have it right here, but
You could
don't know.
replace point counting with an Euler characteristic and some sort of mixed characteristic. I guess I meant concrete application to include things a little different from point counting.
Well, I think so. Sorry. So I think one of the concrete applications was of the BMS, maybe BMS1 work, was that you can say something about if you have a variety in mixed. So I don't know if this is entirely answering the question, but I think one of the applications was that you can make a relationship between the so if you have a variety in mixed characteristic, schema in mixed characteristic, then the Derived homology of the special fiber, the mod P Derived homology of the special fiber is an upper bound. The dimension is an upper bound on dimensions for the Akhil homology, the mod P Akhil homology of the generic fiber. So there was something. So that was sort of a concrete application.
Great.
I don't know about sort of a refined Euler characteristic type application, but I can try to dig out. I don't know if this is exactly relevant, but I can try to dig out later the p-adic Hodge theory application to rational points.
That sounds cool, group too.
Any other questions? All right. If not, I'm going to unmute everyone's mic so we can thank Akhil one more time. So thanks very much again. Okay. And that's it for the mini course for this semester. We are likely to try this again in the winter 2019, different speaker, different topic, and you'll get an email about the plans for that in the future. Okay, thanks everyone. Bye.
Okay, thanks.